All right, guys. So the difference on this one from the last one is is that we need to make the feasible region first. So it's not given, right? Instead, we have these. They're called constraints. So when it says maximize z equals 4x plus 3y, again, that's called the objective function. That's the thing we want to maximize or minimize. In business, maybe it's profit. We want to maximize profit. Or maybe it's a cost function. We want to minimize costs, something like that. And then you've got these constraints. And the constraints are that system of inequalities that we graph. You graph the system and it gives you the feasible region. So one of the problems that I've used before, I've probably used it on a test. It's probably one of the textbook ones too, actually. Is maybe it's a bakery and you make cakes and cookies, and if that's the case, then your z, this objective function, maybe it's a profit. Maybe you get a profit of like $4 for each cake that you make, and maybe you get a profit of $3 for each batch of cookies that you make. And so, X would be like the number of cakes, Y would be like the number of cookies. Um, these constraints then are like limitations. Maybe you have one or two ovens, and there's only so much oven time, and maybe a cake takes 2 hours in the oven, and a batch of cookies takes 3 hours in the oven. I know that's probably not realistic. Again, I'm just applying an application to a problem that wasn't made for it, but you get the idea. And maybe there's only 6 hours of oven time available, right? So like then 2x plus 3y would have to be at most 6, right? And then maybe there's somebody who does the icing, like the decorating with a piping bag, and maybe it takes them 4 hours to pipe a cake, and maybe it takes 1 hour to pipe a batch of cookies. Again, I know maybe it probably doesn't match reality, but you get the idea. If you only have 6 hours of a piper available, then then you have that inequality. So that's the idea here. This is where this is going to go tomorrow when we start getting into some applications. Um, and then the other thing is, like, you can't make a negative number of cakes and you can't make a negative number of cookies. So those two constraints are very, very common, X and Y, both greater than or equal to 0. The other thing I'll point out is this with X and Y only allows us to have two products, cakes and cookies. So if you're running an actual bakery and you make a lot of different things, or if you have a factory and you make a lot of different things, you're going to need more variables. And since we're graphing with X and Y, the graphing gets difficult. If you go to 3, it can still be done in 3 dimensions, but we won't do that. We'll switch. That's where we switch to the matrix approach that I've mentioned, and that's later this week. We'll get into that. Anyway, the only difference here from this and the last one we did is we just have to draw that feasible region first. So I need to graph this system of constraints and then find the corner points and then plug them into the objective function. So you're just going to graph these linear inequalities. When I look at that first one, you can do however you want to do it. If you want to solve for y and do slope-intercept form, that's fine. I notice, though, that 2 and 3 are both factors of 6. So it's like, I feel like it's asking me to use the intercept method, which is, if I plug in 0 for y, I get 2x equals 6, x equals 3, right? So 3, 0 is a point on my graph of that line. 1, 2, 3. And then I can do the same thing the other way. If I put in 0 for x, 3y equals 6, y equals 2. So when x equals 0, y equals 2. That's another point on that line. 1, 2. Okay, if you'd rather put it in slope-intercept form and graph it that way, totally fine. You should get the same graph as me. And but 2 points is enough to graph a line, right? So there it is. That wasn't that good, but you get the idea. All right, and then I could do the same thing here, or this one kind of looks like it's primed for slope-intercept. If I just subtract 4x to both sides, then I get, y equals negative 4x plus 6, right? Y-intercept is 6, slope of negative 4. Oh, I should label this line. 2x plus 3y equals 6. That's what that linear equation is, so I don't mix it up later. All right. On this other one, I need a, here, I'll use a different color. Let's make that blue. And I need a y-intercept of 6. I'm at 2 here, so 3, 4, 5, 6 y-intercept. And a slope of -4. So if I go down 4, it takes me to 2 over 1. Puts me right there. If I went down another 4, well, if I go down another 2, I would just go over a half. So that'll put me on the x-axis. That's actually pretty useful. That's my x-intercept there. So I want this line. Not perfect, but it's all right. And this is the line y equals -4x plus 6. And then, of course, greater than or equal to 0 for both x and y. And I'm trying to shade the region. Now, this is a little tricky. I don't know, like, do I want this region? Do I want this region? Do I want this region? Do I want this region out here? Could really be any of those if you don't, before you look at the inequalities. How do you, let's just do one at a time. If you go back to the one I graphed in red here, this one, how do you know which side of that line to shade based on the inequality?
Well, isn't it like whatever your variable is, like if it's greater than, then you do it above the line. But if the variable is less than, you do it below the line.
Okay, which variable are you thinking of? You're onto something here.
For the first equation?
Yeah, the 2x plus 3y equals or is less than or equal to 6. Are you focusing on x or y, do you think?
I don't know.
If you were going to solve it, which one would you normally solve for?
Usually y.
Usually y. And so the above or below works there.
The slope.
Yeah, to slope intercept form. And you don't have to put it in slope intercept form to do what you just did. You're right. But let me just say, y is the up-down variable, right? It's vertical, right? The y coordinate. And so because y is less than, and notice it's a positive y, that matters, positive 3y. So a positive y is on the less than side, then yes, you can actually shade below, just based on that, if that makes sense to you. I'll tell you another way to know in a minute. If you're not totally sure on that, if you want to isolate y first and actually divide by 3, that also works. Then you'll see y is less than. So the y values that are less are below the line, right? So it could be, like if you graph the whole thing, you'd be graphing all of this, right? Or shading all of this, right? And then you could use the same logic on the blue one, right? Like you could say, okay, y is on the less than side. That's a positive y, right? And so below that line also. And so we're shading down here. And then also we want greater than 0 for both x and y. So like greater than 0 for x. This gets messy if you do all of this, right? And greater than 0 for y. And those all intersect. I'm going to erase like all this in a second. Those all intersect right in here, right? That's like our region right there. Okay, so you don't necessarily have to shade everything like I just did to do it. You can kind of use that logic of, again, positive y is less than on this line, positive y is less than on this line. So we're beneath those two lines and we're above and to the right of the two axes. So that's this region right here. And we just need to recognize that that is our feasible region in there. Does it make sense? One more way you can do it besides the like y is less than, you can do a test point, right? So on each inequality separately, you can test it. What's the easiest point that I could plug in and test? And it works on both of these because it's not on either line. Gosh, 0, 0 is right. Yeah, you can plug in 0, 0. And if you do, we like the 0, 0. All right, if you do, you get 0 is less than or equal to 6. Is that a true statement? Yes, right? So 0 should be on the shaded side. And that'll also be true on the next one. If you plug in 0, 0, you get a true statement. So it should be on the shaded side of that one. And then, of course, above and greater than or equal to 0 for both x and y gives you the same region. So that works too. Whatever you need to do to get there. But that shading that region, that's what you guys were doing in the remote work assignment the other day. All right. So all we need now is the corner points, and we know a few of them already. This is 0, 0, and this one is 0, 2, right? And then this one I was paying attention when I was graphing and I was thinking about the slope. So I knew that was at 1.5. That was like 3/2. So 3/2, comma 0. But if you weren't sure about that, I'll just point out it's where the blue line, which was this one, intersected the x-axis. So if you set y equal to 0 and solve, right, that'll give you that x coordinate. Does that make sense? X-intercept of that line. All right, but I need one more corner point. I need this corner point right here. How do I get it? Yeah, we want this system of two equations right here. We need where they intersect. So you could solve on one of them for y maybe and sub into the other one. Or you could use elimination. Or heck, you could set up a matrix and put it into reduced row echelon form if you want. That might be overkill for this, but it'll work. Any way you want to solve that system of equations, you know lots of ways now. And so again, we have y equals right here. I would probably just substitute this in for the y here. Is that what you were getting at, Amelia? Yeah, pretty much. And so then we get 2x plus 3 times negative 4x plus 6 equals 6. Notice I'm saying equals, not less than or equal to, because I want where they're, like, I want on the two lines where they're equal to each other. And so, yeah, just we substituted one into the other, and now we can solve for x. 2x minus 12x plus 18 equals 6. Negative 10x equals negative 12. X equals 6/5. And then you can substitute that in probably into here for x because y is isolated. And I'll get y equals negative 4 times 6. That's negative 24/5 plus 6, which is 30/5. And I actually get 6/5 for y also. And so that corner point is 6/5, 6/5. Okay, so I have 4 corner points. I have an objective function. I want to find the maximum. So now we do it. Right? I've got x comma y, 0, 0, 0, 2, 6/5, 6/5, and 3/2, comma 0. And then my objective function was z equals, what was it? 4x plus 3y. Thank you. And so when we plug these in, we're going to get 0 here. We're going to get 0 plus 6 here. We're going to get, what, 24/5 plus 18/5 here, which is 42/5 or 8.4. And 3/2. We're going to get 6 here, right? 3/2 of 4. And yeah. So my maximum is what we wanted here, and it's this. It's 8.4, and it occurs at the point 6/5, 6/5. So that's what I would say. I would say Z max equals 8.4 at 6/5, 6/5. Good. So I gave you guys, I think, 4 of these to do tonight. 1 where the graph is already done for you, and 3 like this. Quantity over quality, right? I'm sorry, quality over quantity. I said that backwards. Not very many problems, but they're involved. And take the time to show the work properly and give a good answer. It's good practice. Cool? All right, and then tomorrow we'll bring words into it. And we'll do that for a minute, and then we'll start into that complicated thing that we'll spend several days on.